Hi, I am Ali Khalil, a graduate student in the Faculty of Engineering and Applied Science at Memorial University of Newfoundland. I will be discussing a topic about design and monitoring a solar system for a small house in Lebanon. This project is supervised by Professor Mohsen Jamil. The project highlights are introduction, literature review, system sizing, design and simulation, installation, system monitoring, followed by a feasibility study, and last but not least, a conclusion. Why renewable energy? Renewable energy is the ultimate choice for the next generation, for sustainable development and to ensure the correlation between life and the environment. As a Mediterranean country, Lebanon has ample renewable energy sources, such as solar, hydro, and wind. Lately, the government promoted solar as an electrification option, especially after the dramatic decrease in solar cost from $8.5 per kilowatt in 2009 to $2.77 per kilowatt hour now. For the literature review, I'll start with history of Lebanese electricity. EDL, or Electricité de Liban, is a governmental public industrial company. It covers it controls 90% of the country's power. It has serious problems covering the total demand due to various reasons. It is functioning now on half number of power plants, 5 out of 10, and those 5 power plants have only 60% capacity. Overall, the Lebanese electricity depends heavily on fossil fuels, 93%, which is also depending on oil prices, resulting 8.1 terawatt-hour of unmet load. This project takes place in Lebanon, Zefta region. According to Atlas Solar, this site has more than 300 sunny days per year, average of 8 to 9 hours of daily sunshine. Global horizontal irradiation is 1930 kilowatt hour per meter squared annually. For system methodology, the system is made up of solar panels connected to a smart inverter. It's also connected to grid, battery bank, and to the load, with miscellaneous as cables, switches, and connectors. As for system sizing, load estimate is a vital part of designing any power plant. First step to do that is setting the load profile of the house by taking all the house appliances, stating the rated power, number of the appliances, and average hourly consumption. After that, using hand calculation method to size the battery bank, solar array, and the inverter. This hand calculation resulted in 4 batteries of GE212 deep cycle, 10 panels of monocrystalline 545 peak watt from Canadian Solar, and one inverter from Growatt Company of rated power 5000 watts. The proposed system is created using PVSys software. PVSys software is a tool developed by the University of Geneva to perform design and simulation of different solar projects. First step of design is set according to the site location, the PVSys will give the optimal orientation of the panels. For this site, it is tilt 30 and azimuth 0 facing south. This figure shows us the load profile while setting it in the program. While this figure shows us the choosing of the system components. Here it's for the battery bank, while here it's for the PV and the controller, which is the smart inverter. After designing, the results as follow. First, the energy available, energy used, and unused energy. So the efficiency of the system is 72.2%, and that is explained in the figure to the right. This efficiency is due to unused energy of battery full or from the PV array losses due to temperature and of the battery loss while charging and discharging. After the simulation got approved, the technical team installed the system as shown in the video below. For system monitoring, a smart data logger is used. As shown in the figure, this small white kit made by Growatt Company, it is compatible with the inverter and it is plugged in it and connected to the Wi-Fi. How it works? So our sources are the PV panel and the battery bank. They are connected to the inverter with the connection of the data logger. The data logger sends the current measurement and voltage measurement by using sensors. And after getting these measurements, it is multiplied and to get the power measurement. All this is taking place in the measurement unit, which is the inverter. After that, the data logger will upload the live data to the IoT server. The IoT server will process the data and then publish it on this site, as shown here in this video. System dashboard. First, the company's Growatt, site name Homzifta, and some details about the site, temperature and time, cloud volume, and irradiance. Now it's 7:45 at the site location, so sun is almost at sunset. In the first scheme we have the power imported from solar, power imported from grid, and then we have the state of the battery, whether it's charging or discharging. If charging, arrow will be downwards. If discharging, it will be upwards. Here we have state of charge is 100%, and as for the load consumption now it's low, 465 watt only. We have the total production of solar per day or per the system for all the time, charge and discharge of the battery, and load consumption. In the energy trend graph, we see that the solar production, load consumption, imported power from grid, and exported to grid. As we see here, we don't have imported power from grid because of energy outage, and we are not also exporting to grid the excess energy as we don't have the multimeter. For the battery information, we have the charge discharge daily graph as shown here, and the battery state of charge hourly. Some system of general information are presented here, and social contribution, where it shows how the system is helping environmentally by reducing the CO2 emission. In the energy sector, we have this graph where it shows power either hourly, daily, monthly, or annual. A feasibility study is a preliminary exploration of proposed project. It was performed for a diesel generator and a solar system to choose which system is more feasible for the situation in Lebanon. As for the generator, the capital cost was low, $3,746, of working hours 1,825 hours, and the generator has three maintenances, minor maintenance after each 250 hours, which is changing the oil, and the major one after 1000 hours for changing the oil and air filters, and the last one is for the overhaul change after 10,000 hours. Generator must be replaced after 35,000 hours or 19 years. The future cost of the lifespan of the project will be converted to the present worth cost. So for the generator system, it is $63,268, while for the solar system, the capital cost is $10,600. It is almost 3 times the capital cost of the generator, but the maintenance is too low comparing to the generator, as it's only for cleaning. For solar, we should replace the batteries each 3.5 years, and for the inverter each 5 years. So the present worth of the system will be $43,932. This figure shows the results of the feasibility study. The solar system is more feasible after 3.5 years. As a conclusion, solar energy is viable alternative to traditional energy sources. Despite high capital cost, it has no operational and maintenance costs, as it has also a unique property of having shared environmental effect by reducing the CO2 emission and limiting the global warming. Moreover, additional in-depth studies on solar panels might be conducted. Thank you for listening. Feel free to ask any question.